Hello everybody. Today is the last experiment, which is experiment number 10, and it is about the transient response of the RC circuit. We need to know how the voltage across the capacitor look like when you charge it and when you discharge it. That's why in this experiment we use a pulse wave. When you look at this wave here, when the voltage is high like this, for example 5 volt, then what happens that we are charging the capacitor. And then after that, when it drops to zero, you don't have a source. Then in this case, the capacitor start to discharge. Then how the voltage across the capacitor look like? When it is positive like this, then the voltage across the capacitor will rise like this until it reaches the maximum. And then after that, it will drop, discharge until it reaches zero, and so on. And we have something called time constant here. The time constant is R times C. This is the time when you charge the capacitor, okay, it will reach 63% of the maximum. Then this is the time required to reach 63% of the maximum. Okay, so let us do this first using BitoSpice, and then after that we will do it using analog discovery board. So let's open BitoSpice. It's a very simple circuit, just a voltage source, capacitor, and resistor. It is. And you need to rotate this one, and this one also, and then connect the circuit. Then you add a ground, okay, and then you need to edit the values. The values according to what we have is, we have here, it is 1 microfarad for the capacitor and 1 kilo ohm for the resistor. And for the voltage source, it is 5 volt, the high is 5 volts, the low is 0, and the period is 10 millisecond, and the width, pulse width is 5, so it is 5 high and then 5 low, and 5 high and 5 low, and so on. Of course, the time constant for this circuit, which is RC, R is 1 kilo ohm, 1000, and C is 1 microfarad, which is 10 to the power of negative 6. Then when you multiply 1000 times 10 to the power of negative 6 will be 10 to the power of negative 3 milli, which is 1 milli, negative 3 seconds, sorry. Then it will be 10 to the power of negative 3 second equal 1 millisecond. And this is the time constant. Okay, let's see how we do this in BitoSpice. So we need to set this function, this circuit now. First, the values are right. This is the resistor is 1 kilo ohm. The capacitor is 1 microfarad. You can change it, of course, if it is different. But you need to ensure that there is no initial value here. There is no initial voltage. So make this 0. Because when you run the simulation and then you charge the capacitor, okay, sometimes you have a voltage across the capacitor. So you ensure that this value is 0. And then here you set the voltage. To set the voltage, you need to select pulse, supposed to be pulse, okay? And you hit transient properties, and you select the peak value to be 5 volt. This peak value, it is 5 volt, and then you accept. And then the period or pulse width here 5 seconds, 5 milliseconds. Okay, the pulse width is 5 milliseconds, and the period is 10 milli. So now we set the source, then we hit OK. Then we have the simulation is ready. Now we just need to set up the simulation. Then go to simulation and then setup. Then you have to enable this OP and transient Fourier and Fourier analysis. Then you click transient and Fourier analysis. Then for this one here, you just set the stop time. A stop time is the time enough to show at least one period, and one period here is 10 milliseconds. 10 milliseconds. Then you need to do at least 10 milliseconds. In the slides and in the manual, I have only one period, but here let's make it 2. For example, that will be 20 milliseconds. Then this will show at least, so it will show 2 periods. Let's see. Of course, you can run it from here, but before you run it, you remember what are the node numbers. For the input, it is 5. For the output is 4. So when you plot the signals, you have to plot 5 and 4. So let's run from here. While, as I said before, while this is in the top like this, there is no active plots. Then you go to edit, and then edit plots. And then you add 4 and 5. 4 and 5. 4 is the output, 5 is the input. Then you hit OK. So this will generate the input and output signal. V5 is the input, okay, which is the orange here, and the blue one, this is the output, the voltage across the capacitor. And here, if you want to see, for example, what is the time constant? We calculated the time constant to be 1 milliseconds before. So here we need to click the value that is almost 63% of the maximum. What is 63 of the maximum? 63 of the maximum is, let's use a calculator, is 0.63 times the maximum, which is 5 volt. So it is 315. So try to see where is 315 in the figure here. So around here, I believe. If you are not sure, you look at the values here at the bottom. It is 3.157, something like this. Okay, so yes, this is the point where the signal reach 63% of its maximum, with a maximum, which is 5 volt. Then you find the second, the time. The time here is what? The time is written here, 998. Okay, 99. So it's almost 1,000. 1,000 what? Micro. 1,000 microsecond, which is 1 millisecond. So this is the time. So it's very close to the ones that we calculated. So let us see what's next in the slide. So this is what we have done this already. The time constant is supposed to be 1 millisecond, as I said. Then we did that. And then after that, we set the simulation, OP and transient response, transient and Fourier analysis. Then we set this one. We make it 20 milli. So that's why in the circuit we show 2 periods. But here in the slides you will see only 2. You see only 1. And then, as I said before, if you find this there's a message, there's no active plots. While it is in the top, you hit edit and then edit plots, and then you select 5 and 4, and you show them. So this is the signal, how it look like. This is the output, and this is the input signal, 5 volt, like this. And to know what is the value of tau, or the time constant, you try to select 60% of the maximum, which is 3.15, and you look at the value here. The value is 996. So it's almost 1,000 microsecond, which is 1 milliseconds. Okay. Next part here, we need to add another resistor, which is R2. R2 equal 1 kilo. So we need to add R2. And then I believe that we just need to rerun the simulation and see if we generate the same figure or not. Let's see. So let's go back to circuit. There it is. And add the resistor. You can add the resistor device R, or you can just copy and paste. So here's R, and then you rotate it, Control R, and then you connect it using wires. Here it is. That's it, and it is 1 kilo. So now what we will see, let's see, if we run the simulation, we will have a different signal for sure. But what is the problem here? What is the difference? The difference is that the voltage, which is a 5 volt, this 5 volt. Now it will be divided between the two resistors, R1 and R2. R1 and R2 are the same. Okay, so the 5 volt will be divided equally between them. Then the voltage across the capacitor will be 2.5 volt. So the maximum voltage across the capacitor will be 2.5 volt. Why? Again, because this 5 volt will be divided equally, 1 kilo ohm here and 1 kilo ohm here. Then you will have 2.5 here and 2.5 here. Then the capacitor will be charged to 2.5, and after that discharge. It will not go to 5 volt. Okay, but before, when you don't have this capacitor, this resistor, okay, the capacitor is acting as open circuit to calculate the DC voltage for the capacitor. The capacitor is acting as open circuit. If the capacitor is open circuit, the voltage here will be 5 volt because you will not have any current in the circuit. So when you don't have the resistor, the capacitor will reach 5, will charge to 5. When you have this resistor, when you don't have the resistor, sorry, the voltage across the capacitor will charge to 5. But when you have this resistor, we expect that the voltage will go to 2.5, and then after that drop. Let's see. So now let's run the simulation and look at the voltage. Okay, what's happening here? What happened here is that we have only one signal, which is V5. Okay, so why? Let us see. When you look at the circuit, after I connected the circuit, the resistor, after I connected the resistor, the node number here changed. Instead of 3, it become instead of 4, it becomes 3. So you need to add 3 now, because before the plot that you had here is V4, V5 and 4, but V4 is gone now because you don't have 4. So let us go back and edit the plot, edit this one and add V3. Then okay, so now you see we have this. This is the output. So the output is here. So as we expect, you see, is this going to what? To 2.5 volt, and then after that will discharge. Then the other resistor that we added acted as a voltage divider. It divides the voltage 50%, 50% on this resistor and 50% on the other resistor. Okay. So now this, I believe, this is the last part in the PitoSpice. Next part is we need to do it using analog discovery.